Okay, so we have come to the last module of your this particular course on analog circuit design. Now, in the last three units, what we have done, we have observed the MOSFET, and we have visualized the different aspects of MOSFET. Like we have used the MOS as an amplifier. Typically, MOS as an amplifier. Then MOS as a resistor, variable resistor. MOS as a current source. If you can remember the three regions operations, I mean rather two regions operations, this triode and the linear, triode and the saturation. Forget about this deep triode region. If I consider these two regions, triode and the saturation. In the saturation region, typically the MOS is acting as a current source, and in the deep triode region, where your drain source voltage is much less than the overdrive voltage, right? Over that region, the MOS can be used as a linear resistor, and that resistance value can be modified by varying this VGS, gate to source voltages. And hopefully, you have observed the use of the current source more than anything else in this particular course. They have used current source as a biasing device, biasing element, and most of the cases you have also used the current source as a load, right? That means what? So whenever you are using a current source, that means you'd like to have a constant current. That is the basic fundamental idea behind the current source. The idea is that whenever I say it's a constant current source, for example, this one ISS, a constant current source, that means this current is throughout. I mean, if I consider over a particular time, over a duration of time, then you'll see that this current is remaining almost constant. There is no change in the current, right? Now, the design of this current source is really very difficult. That means a particular design that will not, I mean, for example, let me consider one ideal current source, as you understand. If I have an ideal current source, then this current value, if I call it I of t, for ideal current source, it should be constant like this, ISS, right? But whenever you design such a current source, so that design should be insensitive to any kind of external disturbances. What can be the external disturbances? For example, suppose there is a change in the supply, right? Because ultimately this current source is getting its supply. There is a constant supply in the circuit, so VDD. That supply is there. From where this current source is also getting the corresponding supply. Suppose there is a shift in the supply, VDD. Suppose there is a change in the temperature. Suppose there is a change in the temperature. Then also you can expect that there is a chance that this value of this current ISS might be modified, right? So as far as the proper design of current source is concerned, this is not at all desirable. This is not at all desirable. We want that this value, this current, I mean this ISS, for the time being, let's assume it's a constant current source. That means over time it will give you a constant value, say 1 milliampere or say 0.1 milliampere, whatever may be the value, that is a constant. And that should not be modified. That should not be modified by any external disturbance. Right? There can be some fluctuation in the supply VDD. There can be some fluctuation in the MOS property, because ultimately you understand that this current source, we design the current source using MOS. There can be some fluctuation in the temperature. Right? So even if those fluctuations exist, but we have to ensure that the current source will be constant, and that design is not that easy. And you understand that in a particular circuit, hopefully last day some of you have attended the class. You have seen that this dimensional amplifier, that one, you look around almost 1, 2, in one side you have 1, 2, 3, 6, 7. 7 the MOS was there for the design of this dimensional amplifier. With current source load, along with that you have a diagonal tail and a tail current. So you have seven MOS devices in a particular circuit. So typically in an integrated cycle, you can expect there are so many MOS devices, right? So if you have so many such current sources in a particular circuit, particular design, then it is not possible to design that very stable current source every time. But that is a requirement. Your requirement is that you have to design some stable current source. Stable current source means what? That means the value of this current ISS should not vary with any external disturbances. the supply variation or the temperature variation or the from mosque to mosque, it will not vary. It will give you a constant. Now that is not easy for so many current sources in a particular cell. You can do it for a single cell. That's great. For a single current source design, that's perfect. You make a so many MOS device so that you can have a stable current source. But your idea or your requirement is not that you have only one stable current source. You require more than one stable current source. So is it justified or is it a wise solution to go for that complicated design, that costly design everywhere in your circuit? It is not at all desirable. That is what people thought. That okay, we design one such circuit that will give you a constant current source, stable current source, constant current source, and then what we do, we just copy that particular current source using some copying circuit, so that we can have so many a number of copies of that ideal current source. And this gives you the notion of current mirror. That means we have some constant current source, a stable current source that you have designed using some complicated circuit, a costly circuit, but you cannot afford this circuit. You cannot have this circuit many times in a particular design. You cannot afford it. That's why what people thought, okay, let's build this circuit. Let's call this circuit as let's call this current source as this I reference, the reference current source, which will give a constant current source, constant current over a time, and then we use some copying circuit using which we can generate a copy of this, right? You understand that during your examination, semester examination, you people normally go to the Xerox. You have to go for this Xerox. Sometimes you go for I'm coming to that. Sometimes you go for 100%. That means there is no change. Rarely go for 200%. Macro zeros, you don't go for that. Right? You don't go for macro zeros. But rather, most of you go for macro zeros, you don't go. But most of the cases you go for micro zeros. Right? That means what? The copy of this. Same thing, but in the size it is reduced. Right? So, the same concept, there is a copying circuit. And you copy it. So it's not that the current that I am calling, say, I require some current, say for example, I reference is equal to say 1 milliampere. That is 1 milliampere. Sometimes you require 1 milliampere current source. Sometimes you require say 2 milliampere current source. Sometimes you require say 0.1 milliampere current source. Sometimes you require 0.5 milliampere current source. So this 1 milliampere current source is a reference current source, right? And using this copying circuit, you can go for the other kind of design, so that ultimately you can have this current, the desired current is some constant k times I reference. This k can be greater than 1, k can be less than 1, k can be equal to, right? Either k equal to 1, k greater than 1, or k less than 1. Okay. So first of all, you tell me, whenever we go for the design of the current source, obviously we have to ensure that the device, the transistor, this MOS, must be operating in the saturation region. That is quite obvious. It must not operate in the triode or deep triode, because if the MOS is there in the saturation region, then only you can expect that this current ID, for the time, if I just neglect this channel length modulation, then this current ID is equal to half into mu and C of W over L into VGS minus VT whole square. If I design this current source using a particular NMOS device, it's NMOS and half mu and C, otherwise it will be mu PC, right? Then what should be there in the copying circuit? What should be there in the copying? How can we ensure that the device is there always in the saturation? How can we expect that the device is there always in the saturation? Because no, VGS greater than that. That is a condition for the MOS to be in the on state. VGS greater than 8 and 10 can be short. Yes, if you short the gate and drain, that's a direct connected model. For example, this is the MOS, and if gate and drain they are shorted, that means gate source and drain source, they are, for an NMOS device, How can you ensure that the device is there in the saturation? That means what? That means the drain can be lower than gate by at most 1 session. Drain can be lower than gate by at most 1 session. Even if they are at the same potential, that means you are in the saturation. The most in the saturation. What is the condition? The condition is that this VGS minus VTH that should be less than VDS so that the device is there in the saturation region, right? VGS minus VTH must be less than or equal to VDS. So if gate and drain they are at the same potential, that means a direct connected model. In that case, what do you expect? You expect that the device will be there in the saturation. Now suppose if you have this kind of behavior, gate and drain they are shorted, and suppose I would like to observe, suppose for example, suppose now suppose I feed a current length, say let it be say I reference, I reference. Okay. Then under this condition, what will be the relation between this I rate and your this particular voltage, say gate to source voltage or drain to source voltage? How does it vary? So mathematically, if I yes, so suppose this one is IDF, that is your input stimulus. Input stimulus is IDF, and this voltage plus minus. Suppose this voltage is say I can call it VGS, no problem because gate and drain are shorted. I can call it VGS. So how does this VGS vary with IDF? Huh? Straight line. How does VGS vary with IDF? No, you can modify this IDF. No? I'd like to observe this VI characteristics. We can do the other thing also. Whenever say IDF is equal to 0, that means what? That means we would like to observe. So suppose here I am varying this IDF. I am varying this IDF. I would like to observe this I versus V characteristics. I versus V characteristics. How does it look like? I am varying IDF also, right? So when IDF is equal to 0, exactly 0, what will be the VG? That is exactly equal to VTH. Less than VTH. So when IDF is just greater than 0, this gate source voltage equal to the threshold voltage, right? So suppose this is the point, for example. Suppose this is the point over here. This is the point, right? Suppose this is your VTH, right? Then as you increase IDF, how does it vary? VGS? How does it vary? You know the formula? What is the formula? ID is equal to half mu. So from this expression, what you can write? This gate source voltage is equal to VTH plus square root of twice ID upon mu1 C of W over L. That is the formula. So here ID is equal to IDF. So how does it vary? Say, suppose like this. It will vary like this. Okay. So that function. So that function, the variation of this red one, this function is this one, right? So VGS is equal to VTH plus square root of twice ID upon mu1 C of W over L. So that is this function. So I am representing this gate source voltage as a function of your drain current. So I can call it this function. I can call it this function as a function of VGS. Or rather this one I is equal to half mu n C ox W over VGS minus VTS square. This one is a function of VGS, and this function can be regarded as the inverse function, f inverse of I reference. This one. This is f inverse function. Now, if I provide the just the inverse of this, if I provide this particular function, this particular VGS as the gate source voltage of another MOS, then what will be the current? The current will be equal to your I reference. That is the idea. This particular function, this is the F inverse function. This is the F inverse function, which relates I reference, which relates VGS as a function of I reference. VGS as a function of I reference. So this VGS can be written as F inverse of I reference. Now, if that VGS, so we have this constant current source I reference, and you have this copying circuit. This is the copying circuit, right? You get some VGS, get source voltage over here, this voltage. Now you feed this voltage to the gate source voltage of the another circuit. And then what will be the current flowing through this MOS M1? This I out is equal to, if I assume that the WI ratio of this MOS and WI ratio of this MOS, if they are same, then this current is equal to the I reference. If not, then obviously there will be some scaling factor outside. Get it out? Okay. Now let's move to the combined circuit. Let's move to the next slide. Now let's observe this. You have this one already we have discussed. This one we have already discussed. Direct connected device. Gate and drain they are shorted. This current is I reference. That means the device, this M1 is there always in the saturation region. That gate source voltage is a function of I reference, and we have already observed this one. What is that? VTH is equal to VTH plus square root of twice I reference by mu n C of WL1. Mu n C of WL1, one of this particular MOS M1. Then got some VGS. Now, if you provide that VGS to the gate voltage of the second MOS M2, source is grounded. What will be the current? We can write this expression I reference is equal to half mu n C of WL1 VGS1 minus VTH1 whole square. Let's assume that both of these two MOS devices, they share the same threshold voltage. So threshold 1 and threshold 2, suppose they are equal. What will be I out? Half mu n C of WL2 into VGS2 minus VTH2 whole square. And somehow we have managed to have same VGS1, and VGS1 is equal to VGS2. This VGS1, gate source 1 is equal to gate source 2, because their gates are connected. Sources are grounded, gates are connected. So VGS1 is equal to VGS2, threshold 1 is equal to threshold 2. So I reference by I out is equal to W by L1 upon W by L2. Right? So now if you can manage that, okay, my I reference is a constant current, double current. If this one is constant, this one is double, then obviously you can have so many such copying devices or copying circuits. And each of them, I out 1, I out 2, I out 3, I out 4, all of them will also be a function of I reference, a constant function of I reference. Why? Because this ratio, this W by L1 upon W by L2, this ratio is no longer dependent on your supply voltage. This ratio is no longer dependent on the temperature. This ratio does not depend on the mu and current. Can you get the point? Typically, whenever I write an expression for the current, in the expression, how many temperature dependent parameters are there? In this expression of this current I reference, we have half mu n C of W by L1 VGS1 minus VTH1 whole square. So mu n is a temperature dependent parameter. Then you have this gate source voltage, the supply dependent parameter, because if the supply voltage changes, obviously the gate source voltage will vary, and this threshold voltage VTH. So if you go by a simple method that okay, I would like to have a MOS, I would like to make it okay. Suppose the MOS is operating in the saturation, say gate and drain they are shorted, and if I have that particular expression, then in this expression you have so many temperature and supply dependent parameters. Like you have this mu1, you have this VGS, you have this VTH. So these three parameters you have, which are either supply dependent or temperature dependent. Now, if I consider this expression, I reference is equal to I out, or I out is equal to I reference into W by L2 by WL1, and if you can expect or if you can manage that okay, this I reference is a constant current, so it's a stable current source, and obviously this W by L1 upon WL2, this is not at all a temperature dependent parameter or supply dependent parameter. So therefore, if your I reference is a stable current source, then so is I out. If I reference is stable current source, so is I out, and you can have so many such copying circuits. Right, because here you don't have any dependence neither on temperature nor on the supply function. Right? But that description that we have arrived over here, I reference or I out is equal to W by L2 upon WL1 into I reference. So that is derivation is carried out with some simplistic assumption. What is that assumption? Please. What is that assumption? The expression that we have got, I out is equal to WL2 by WL1 into I reference, that is obtained with some simplistic assumption. Okay, VTH one equal VTH, that's fine. No, okay. No, not this one. Not this one. We have neglected the channel length modulation. We have neglected channel length modulation, and now you understand that you cannot neglect channel length modulation for a short channel device. Right? What we have done, we have somehow managed that okay, the sources are connected together at ground and gates are connected together. So VGS1 is equal to VGS2, but these voltage sources are connected together fine, but these drains are not connected together. These drains are not connected together. So VDS1 is equal to VGS1 is equal to VGS2. That's great, but that is not equal to VDS2. VGS1 is equal to VGS2 because gates are connected together, sources are connected to ground, and the first MOS M1 is in direct connected fashion. So drain source 1 is equal to gate source 1. VDS1 is equal to VGS1. That's great. But VDS1 is not equal to VDS2. But in the expression of I reference or I out, what you have? Apart from this one, you have 1 plus lambda VDS down. So typically what we have? Typically we have this kind of thing, no? 1 plus lambda VDS2 by 1 plus lambda VDS1. Even if the lambdas are same, but drain source 1 and drain source 2, these two voltages are not the same. Or we can write this drain source 1 as gate source 2. So drain source 2 upon gate source 2, these are not the same. So therefore, if I incorporate the channel length modulation, then the I out value is no longer a constant function of I reference. So although it looks very simpler, the basic circuit to start with the current mirror circuit, but gradually we have to modify it. Is it clear at this point? This connection? Yes. So as to ensure that this MOS is there in the saturation. Always in the saturation. Is it clear up to this point? Huh? Is it clear up to this point? Now we move to little bit complicated circuit. Don't get afraid of this. What we have done? We have got this circuit. As of now, we have got this circuit. Right? What we have done? We have added another MOS. M3 on top of M2, right? What is that? Can you identify this connection? This connection? The cascode connection. What is use of cascode? What is use of cascode? Or one of the, just tell me one of the properties of cascode. What about the output impedance for cascode? Huh? What is the implication? For cascode, the output impedance is very large. What does it mean? What does it mean? No. Here you don't go for amplification. For cascode, your output impedance is large enough. That means even if I have some fluctuation over there, that will not be reflected over here. So that this point, this potential at this point can be made at a constant value. You have to check this. How to check? How to check? For checking, I need to draw the corresponding small signal model of this part. This part only. This part. M3 experiences what? What is that? So from P to B, you have this RO3, right? And then from B to this, because whenever you go for the small signal analysis, and this is held at a constant voltage, that means this is equivalent to AC ground, right? So therefore you have another 1 by Gm plus Gmp, 1 plus Gm plus Gmp from this point to ground, and apart from that the resistance of this particular MOS, say let it be Rm. So now if you have some fluctuation over here, how will it be reflected at this particular point? A simple voltage division law. What is that? You have 1 upon Gm plus Gmb, Rm2, they are in parallel, and along with that you have RO3 is in series. Okay? Now if I call this parallel combination, this 1 upon Gm3 plus Gmb3 and Rm2 is equal to R effective, then this R effective is given by this one. Then what about your delta Vb? This delta Vb is equal to delta Vp multiplied with R effective by R effective plus RO3. Right? Now, after simplification, what we are getting? This one. Delta Vp is almost equal to delta Vp by Gm3 plus Gmp3 multiplied with R. Is it large? This one? Is it large? GMRO? Typically large? 10 to 20, typical value 10 to 20. So therefore, even if we have some fluctuation at the point P, that will not be reflected at point P. So if I manage some constant voltage at point B, that will not be modified to some extent. Even if the voltage at point P experiences some change. So what is our objective? Our objective is to provide a constant voltage at point B. We have got this circuit. And now you have to find out what should be that voltage. So this circuit is good enough for providing you current mirroring effect, copying circuit, and now you have to find out what should be that particular potential. Remember that all these three, okay, this M1 is already in the saturation. You should not be bothered about this M1 because gate and drain they are shorted. But you have to ensure that this M2 and M3, they must be in saturation. Okay. So for that, the same circuit. First we consider this one. This circuit already I have observed. This is the previous circuit. right? What was the bottleneck? Drain source 2 by drain source 1. Drain source 2 by drain source 1. If you can remember, 1 plus lambda VDS 2 by 1 plus lambda VDS 1. Source 1 and source 2 they are connected to ground, fine. But the drain 1 and drain 2 they are not connected. So what you have to ensure, you need to ensure that this drain 1 potential and drain 2 potential, they should be same. VA is equal to V, right? For which, what we are doing? For which, how can we expect that V is equal to V? So what is that? Yes, so if I observe over there, so V3 minus the gate source of V3 minus gate source of 3 is equal to VB. V3 minus gate source of 3 is equal to VB, and that has to be equal to VA. So how can you get V3? How can you get V3? V3 is equal to VGS3 plus VA. So here already have got some VA. So from VA, how can you synthesize V3? So if you can add another gate source voltage to this VA, then you'll be getting V3. Right? So therefore, on the top of this particular MOS M1, you can add another MOS. Like this. I call this MOS as MOS 4, M4. Previously that one was there, this potential. What is that potential? That is equal to VA. What we need to ensure? We need to ensure that, if you can remember that expression, you have 1 plus lambda VDS 1 by 1 plus lambda VDS 2. Because of which this constant function was not present. So what I need to ensure? Okay, source 1 and source 2 they are connected to now. I have to ensure that drain out and drain 1 they must be at the same point. So that means, what is the drain 1 potential over there? That is the potential at point A. What is the drain 2 potential? Potential at point B. So what I need to ensure? I need to ensure that VA and VB they must be same. Now accordingly I have to select this particular value V3 because a cascade kind of thing. So what is V3? V3 minus gate source 3 is equal to your VB. VB is basically the source potential of M3 or the drain potential of M2. Right. So V3 minus VGS3 is equal to VB. That is equal to VA. So therefore V3 is equal to VGS3 plus VA. Okay. So on the top of this MOS M1, I need to add another MOS. Right. And once I add this particular MOS, then from here to here, what is the voltage? Basically the gate source voltage. Already have VA plus I require another gate source voltage. So you have VA over there, and from here to here you have another gate source voltage, and that voltage has to be equal to the V3 voltage. Okay. So if you observe from this side, what is V3? VGS4 plus VA. Right? This is VGS4, right? And VA. From this side, what is that voltage? VGS3 plus VP. What I need to ensure? I have to ensure VA is equal to VP. That I need to ensure. Right? So therefore, VGS3 plus VP is equal to VGS4 plus VA, and I have to ensure that VB is equal to VA. That means what? You have to make sure that VGS3 must be equal to VGS4. How can I make sure? So VGS is equal to VGS4. Remember, the current which is flowing through this path is I reference. The current which is flowing through this branch is equal to I out. Okay. So therefore, what I can write over here? Half mu(c) of W over L multiplied with, obviously here you do some approximation. We don't use this your channel length modulation there. So half mu(c) of W over L multiplied with VGS4 minus VTH whole square is equal to half mu and C of W over L multiplied with VGS1 minus VTH whole square. These two are same. Left hand side and right hand side, they are same. Like this. Yes. Now, to some extent, it is much more approximate. This one, as compared to the last level. Even if this is not perfect. Even if this is not perfect. We will once again modify this double. Initially, we have started with only two modes, M1 and M2. Then we understand that okay, there can be some fluctuation of the drain potential of M2. So I have to ensure something. I have to make sure that this potential should not vary. How can this be ensured? For which we have added one such MOS on the top of the second MOS M2 in transport fashion, so that during some fluctuation is there and node P that will not be reflected at the drain of the second MOS M2. Then the next question comes: how can you find out the gate potential of this second MOS? I mean this MOS 3 M3, for which we have added another MOS in the left hand side. Okay, now if you go by this formula, obviously this current is equal to this current is equal to your I reference, and this current is equal to I out, right? If you divide this by this, equation 1 upon equation 2, then what you get, assuming that the threshold voltage is the same, what you get? WIL1 multiplied with VGS1 minus VTH1 whole square upon WIL2 VGS2 minus VTH2 whole square is equal to WIL4 VGS4 minus VTH4 whole square upon WIL3 VGS3 minus VTH3 whole square. But I need to ensure, already I know that VGS1 is equal to VGS1. That means this gets cancelled. And I have to make sure that these two are same. So therefore, what is the condition? The condition is that WIL1 upon WIL2 is equal to WIL4 by WIL2. If this condition holds good, then I can have this entire thing, right? So let me go to the So that is the condition. 1 by 2 is equal to 4 by 3. 1 by 2 is equal to 4 by 3. If this condition holds good, then I can have this current copying. Still, since we have added something on the top of M2, what will be there apart from that? Okay, that's great that you have got something. You have copied the current. Okay, that's great. But what's the limitation out of this particular arrangement? Can you find any such limitation? The color body. You add something. Is there anything related to loading? Something, because we have to ensure that all these four MOS devices, all of them, 1 and 2 they are in saturation, fine. But you have to ensure that 3 and 4 has to be in saturation, and that severely restricts the available voltage. Right. So let's have a look at this. What is the minimum voltage? Because now we have two circuits. We have two circuits. Circuit number 1, circuit number 2. In circuit number 1, I have to select the value of D3 arbitrarily in trial and error, so that this M3, M2 they are in saturation. Right. I can select it arbitrarily. Under this condition, what is the minimum value of the potential at point P? What is Vp minimum? What is Vp minimum for circuit 1? What is that? So first of all, this voltage at least it should be the gate voltage minus The threshold voltage, right? And once again, this voltage, what is this voltage? What is the minimum value at node B? What is the minimum value at node B? Gate voltage minus threshold voltage overdrain voltage. So summation of two overdrain voltage, right? So now if I consider this one, second circuit, first circuit, this is nothing but VGS3 minus VTH plus VB. What is that? VGS3 minus VTH plus VGS2 minus VTH, because V minimum is equal to VGS2 minus VTH. So the minimum value for Vp is given by the summation of two overdrain. What about for the second circuit? Second circuit, V3 minus VTH. Had this been V3 minus VTH, so how can we represent V3 in terms of the other elements? What is V3? What is V3? This voltage. How much? This voltage, how much? VGS4 plus VGS1, right? This one is VGS4, this is shorted, this is VGS1. So V3 is equal to how much? VGS4 plus VGS1. And what was your VP minimum? This drain voltage minus this gate voltage minus the threshold voltage. That is the minimum drain voltage. So that M3 remains in saturation. Right. So V3 minus VTH. What is V3? VGS4 plus VGS1 minus VTH. Now you can represent this one as VGS3 minus VTH plus VGS2 minus VTH plus VTH, or VGS4 minus VTH plus VGS1 minus VTH plus VTH. So it is the summation of two overdrive voltages plus another threshold voltage. So which one is preferable out of circuit 1 and circuit 2? In circuit 1, you have observed that VP minimum is the summation of two overdrive voltage only, and for circuit 2, it's a summation of two overdrive voltage plus addition of threshold voltage. So which one is preferable?
Basically, first swing and
Yes. So first circuit is preferable. Circuit 1 is preferable because here you have the minimum, because you know the maximum value can be VDD. So minimum should be as small as possible. So here minimum is the summation of two overdrive for circuit 1. But as you have made the circuit much more complicated, so that you can have much more accurate VDD. At the cost of what? At the cost of less voltage. So this circuit, so the first circuit, so now we have got these two circuits, circuit 1 and circuit 2. So in the first circuit, V dash is poorly defined, so less accuracy. V dash is poorly defined, less accuracy, but the voltage headroom is also less. We have more provisions for swing. What about the second circuit? V dash is properly defined, but the voltage headroom is also high. So you have less swing, right? So there is a trade-off. In circuit 1, accuracy is less, swing is available, swing is more. Circuit 2, accuracy is more, but swing is less, right? So can you go for a circuit which gives accuracy, allow voltage headroom? So what is the minimum VP minimum? What do you expect? That is the summation of two overdrive. We can't afford summation of two overdrive or addition of overdrive, because circuit 1 provides you summation of two overdrive. So you are happy with summation of two overdrive, but that V dash or that V3 has to be properly defined, right? So then don't get afraid of, I'm telling you once again, don't get afraid of. Let's consider a part of this is not the entire circuit, it's a part of the circuit. What you have done? There is a feedback. There is a feedback from the output to the input, right? We need to ensure that M2 has to be there in saturation. What is the condition for that? What is the condition? So that M2 remains in saturation. Condition is that this gate voltage minus threshold should be less than drain voltage. What is the drain voltage? That is Vx. So the condition is V dash minus Vth2 must be less than Vx. What is Vx? Vx is nothing but Vgs1, right? So V dash must be less than or equal to Vgs2 plus Vgs1 plus Vth2. I need to ensure that M1 has to be in saturation because we are dealing with current mirror circuit. So all of the MOS devices they should be in saturation. What is the condition for M1 to be in saturation? This voltage over here, this voltage get to source minus threshold 1 should be less than or equal to the drain to source voltage. What is the drain to source? Let it be V double dash. So this one V double dash. What is the relation between V dash and V double dash? V dash minus Vgs2 is equal to V double dash. V dash minus Vgs2 is equal to V double dash. So I simply plug in the values over there. V dash minus Vgs2. So then that will give you the lower limit for V dash. This is the lower limit for V dash and this is the upper limit for V dash. So V dash is bounded between VGS1 plus VGS2 minus VTH1 to VGS1 plus VTH2. So accordingly you have to select the value for V dash. So you can have some feasible value for V dash if this value is less than this value, then only feasible, otherwise not. What is the condition? The condition is that VGS1 plus VGS2 minus VTH1 should be less than VGS1 plus VTH2. So VGS1 gets cancelled and ultimately what you have VGS2 minus VTH2 should be less than the threshold voltage. So therefore the overdrive for this MOS should be less than one threshold. Right? This is a part. This is a part of the coupling circuit. Still, I have to synthesize this V dash. I need to synthesize V dash. The condition is that V dash has to be there within that. That means V dash must satisfy that particular inequality condition. That means VGS1 plus VGS2 minus VTH1 should be less than V dash, should be less than VGS1 plus VTH2. If this condition holds good, that means you can have some value of V dash for which both M1 and M2 they are in saturation. So you have got some limit, upper limit, lower limit. Okay, but how to feed the value for V dash? What should be the V dash value? What should be the actual V dash value? How can you get this V dash? From where? Still this particular node is left blank. It has to be connected somewhere else. Right. That circuit you already observed. I have told you this is a part of the circuit. The part of the circuit. So this is your basically this copying circuit, and then you have this I out circuit. I mean the copied circuit. This one and this one. You have started with this, huh? You have started with this one. I mean not this one rather. Yes, you have started with this one. Then we have added another MOS on top of this. We have added another MOS on top of this. Ultimately, we have got these two circuits, circuit 1 and circuit 2. One circuit is these two circuits. This circuit is less accurate, but it has high availability. On the other hand, this circuit, circuit 2, is more accurate, but less availability. Then what we are doing? We have modified the circuit, the left hand side of this particular circuit we have modified, and accordingly we have come to this one, this circuit, and this is a copying circuit, part of the copying circuit. And this is your I out part. This is the cascode configuration. When I identify this customer part, this one on the top of M3 you have some M4 like this, and we are in the process of getting this B dash. If you can remember, we are in the process of synthesizing this B dash. Still, it is right at this moment we have not synthesized this value. We know that okay, this is the range of B dash. VGS1 plus VGS2 minus VTH1 should be less than B dash, should be less than VGS1 plus VTH2. That is the range, minimum and the maximum value, upper and lower limit. But still, this one we need to synthesize this B dash. Right hand side is okay. M3 M4 combination, that is okay. Still, we have to synthesize this B dash value. For which, that is the final part. I think you can simply expect that this condition must hold good, because through this branch the current is I reference, through this branch the current is I out, so that condition must hold good. This condition, yes or no? Yes, this condition must hold good. So for 1 and 3, you understand that get source 1 is equal to get source 3. That is quite obvious. Gates are connected together and sources are connected to ground. So VGS1 is equal to VGS3, and I need to ensure that this VGS2 must be equal to VGS4. VGS2 must be equal to VGS4. So therefore, in order to ensure that VGS2 is equal to VGS4, that condition must hold good. WL1 by WL3 is equal to WL2 upon WL4. Okay. So that is the last line. This is the last line. So we are in the process of synthesizing B dash. That B dash was still, this is an open node, right? B dash is still an open node. So then what we are doing? So that part, it looks little bit complicated. We have added 5, 6, 7. 3 more mouse devices. Out of them, M5 and M7, they are in direct connected fashion. M5 and M7, they are direct connected. And this condition, you have already observed now. The feedback, output to input, with one restriction, that this VGS7 minus VTH7 for this one, MOS7, this is small enough. This is small enough. What is the advantage? If this is small enough, we have the same current, same I reference flowing through M7, M5, M6. Same I reference is flowing. Now, if the gate minus threshold is small, what does it mean? How can I ensure that this one is small? Same current, same V1, same Cox, but the VGS minus VTH7 is small. That means what? You have to make WL7 large. What is the advantage of making this VGS7 minus VTH7 small? That means this difference, you can consider this difference from here to here, you can expect that this difference is equal to, this is small enough, that means this difference get source minus threshold VTH7 small, so that difference is equal to VTH7. So now under this condition, once again, if you would like to find out the value of V dash, what is that V dash? What is V dash? Over here, VGS1 plus VGS2 minus VTH. The same thing that we have done last time. But under this condition, what will be your VP minimum? What will be your VP minimum?
M6 on or condition
M6
on or condition.
Yes.
V dash to the potential M6 forms it are in potential.
Which potential?
M6 is ready. Gate potential.
M6, the gate potential of is V dash. Yes. What is the minimum value. What is the minimum value for this VP? What is VP? What is VP? VP minimum. That value over there. What is the minimum potential at point P? Gate voltage, drain voltage. What is the minimum value for this? Gate minus 1 threshold. That means V dash minus VTH, because this voltage is V dash. MC and M will be connected after that. We are just considering the shopping circuit. That part is there, still there. Because as I told you, that we are in the process of, this MC and M will be there. We are in the process of synthesizing this V dash, right? What is this VDS6? You have to ensure that all of them must be in saturation. M7, M6, M5 is in there in saturation because gate and drain they are shorted together. M7, so as M7. So as M7. So what is your VDS6? How can I represent this VDS6? How can I write VDS6? VDS6. How much? How can I write it? VD6 minus VS6. Right? What is VD6? How can you represent this VD6 in terms of? How can you represent VD? That is V dash. How can you represent this VD6 in terms of? In terms of the gate potential of MOS7. Gate potential of MOS7. Is it possible to write? Then VD6, I mean over here, what is that voltage? What is that voltage? This voltage is this voltage minus this one. This voltage minus this one. What is that? What is that? I can call it, say, G7. This is nothing but your V G7 minus VT7 minus VS6, and 6 and 7 their gates are connected. 6 and 7 their gates are connected, right? So I can write like it's VG6 minus VS6 minus VTH7. That means what? VGS6 minus VTH7. This one. VDS6 is equal to VGS6 minus VTH7. Okay. Then what is V dash? What is V dash then? What is VDS6 plus VDS1? So V dash this one this one plus VDS1. That means VDS6. These two are connected plus VGS5. V dash is equal to VDS6 plus VGS5. What is VDS6? VGS6 minus VTH7. So therefore I can write V dash as VGS5 plus VGS6 minus VTH7. Okay, once I get this V dash and I know that what is my VP minimum, V dash minus VTH, then it comes out to be VGS3 minus VTH3 plus VGS4 minus VTH4. That means the summation of 2 over 5. So we have got ultimately the summation of 2 over 5. This voltage, this VP minimum, summation of 2 over 5, but at the cost of what? So this circuit is much more stable, obviously stable, accurate, and higher swing. But at the cost of what? Nothing is obtained at free of cost. At the cost of what? At the cost of more? At the cost of more number of MOS devices. So you have more power loss. Right. So this ends the basic discussion, the fundamental discussion on this current mirror circuit, and as of now we have used or we have observed how can I use the coupling circuit in order to obtain the different versions, different copy of a fixed stable current source. And in each of these cases, we have used the current source as a load on, right? As a load on. And gradually we'll also see how can we go for this design of active source. So this is nothing but your design of passive current mirror, and we will in the subsequent classes we will also observe how can I have the design of active current.